Hello, thank you for logging in to session 24, topic number 2. I would like to thank in advance my session chairs, Paul Tinner and Jen Vardaman, for hosting this session. My name is Jacinta Aman Lim, and I am the Technical Director for Business Development at Nepes Corporation. I am based in San Diego, California. I will be sharing with you a presentation titled 600mm Fan-Out Panel Level Packaging as a Scale-Up Alternative to 300mm Fan-Out Wafer Level Packaging with 6-sided die protection. This presentation will be divided into several sections. I will cover a brief introduction into the motivation for utilizing 600mm by 600mm square panel for 6-sided die protection, panel layout segmentation for back-end processing equipment fungibility, key package attributes, process areas for consideration on 600mm Fan-Out PLP, package reliability, namely component level reliability, cost considerations for 600mm FOPLP, and to end this presentation, a summary of our findings. While Fan-Out Wafer Level Packaging has been established as one of the most versatile packaging technologies, traditional 300mm or 330mm round carrier used for processing Fan-Out Wafer Level Packaging is still cost inhibitive. As the demand for PMICs, RF, and other single die applications increases for Fan-Out Wafer Level Packaging on mainstream carrier sizes, large panel level processing to meet these demands become a natural progression to an already burgeoning market. However, not all products would benefit from migrating from a 300 or 330mm panel to larger panel sizes. If total area of the panel is not fully utilized, it results in material waste and loss. Utilizing 600mm by 600mm panel size for Fan-Out PLP while utilizing existing equipment for back-end processing can help minimize costs for panel size migration. Scaling up from 300mm or 330mm carrier sizes will require front-end equipment processing investment and high-volume silicon source, also known as customer, supply for fan-out devices. There are many versions of fan-out packaging. However, fan-out processes can be divided into two major categories, which are chip first and chip last. In the chip first process, singulated die is placed first onto a temporary carrier, goes through compression molding process, and subsequently the appropriate thin film processing steps. In the chip last process, a temporary carrier will first undergo thin film processing for RDL definition before singulated bump die or copper post is placed on the corresponding RDL area for terminal contact. Within the chip first and chip last, there are various subsets. We will focus on chip first processing in this presentation. The subsets in chip first fan-out wafer level packaging is either die face down or die face up. With die face down, one variation is EWLB. With die face up, we have the M series. For illustration purposes, I am using two examples in this table to compare with chip last. For all the options, incoming wafer, either in 200mm or 300mm format, will first need to go through singulation process. For M series, a copper stud process will need to be completed first on incoming wafers. Die will be placed face up on the temporary carrier, copper studs facing up. For EWLB, back-end processing such as back grind, singulation, will need to be completed before reconstitution process. Die will be placed face down onto the temporary carrier. One key item to note for EWLB is that mold compound material is not protecting the active side of the die. In comparison to flip chip CSP, flip chip BGA, and wafer level CSP, the fan-out structure provides scalability to significantly increase routing density, while the thin film process provides a reduction in package size and thickness as opposed to substrate-based packages. Fan-out in comparison to wafer level CSP has higher board reliability, lower thermal, and the potential for integration of multiple dies, 3D package on package, and system in package. In comparison to wafer level CSP, we've taken a look at board level reliability for temp cycle for the six-sided die protection package. The baseline is 2P2M, which is PM1, RDL, PM2, and UBM for both molded die and wafer level CSP. The die size is 6 mm by 6 mm. When same dies is used in the six-sided die protection process, the body size now becomes 6.15 mm by 6.15 mm. The fan-out package is 350 micron ball pitch with Seg405 ball. Both wafer level CSP and fan-out use the same Seg405 solder. 1 mm thick JEDEC test board was designed for the BLR evaluation. From this chart, we found that temp cycle for 2P2M for the fan-out package improved more than 60% in comparison to wafer level CSP. 1P2M improved more than 30% in comparison to wafer level CSP. And BLR for 2P1M improved more than 10% in comparison to conventional wafer level CSP. As cost is one of the big hurdles with fan-out, a broader adoption of fan-out to drive down the cost of the technology comes into play. The natural progression would be to scale up from 300 mm or 330 mm round panels to 600 mm by 600 mm square panels as an alternative to cost reduction. The 600 by 600 mm square panel size for Fan-Out PLP was chosen to maximize capital productivity in wafer processing that would be segmented into 4 300 mm square panels for subsequent process steps. Final electrical tests can be performed on a 300 mm square segment utilizing existing 300 mm wafer probers. In addition, 300 mm square segments can utilize existing 300 mm background equipment for panel thinning with minor upgrades. Let's take a look at panel segmentation on the 600 mm panel. In general, a 600 mm square panel can accommodate upwards of 5 200 mm wafers. Some considerations to take into account for maximizing gross die per panel are segmenting the panel into 9 200 mm squares or 4 300 mm squares for backend processing. Our goal here is to minimize costs of manufacturing as much as possible to ensure backend tools such as testers, backgrind, saw, ball chop process, or laser marking are fungible with wafer level CSP production in the factory. Total usable area loss was calculated by subtracting sum of package placement, zone fiducial die, and package ID from total panel area. In this example, option C has calculated usable area loss of 2 times more in comparison to option B. As we get into larger package sizes or multi-die packaging for panel level packaging, the positive impact of 4 versus 9 segments on a 600 mm panel would be larger due to keep-out zone and placement of the die to maximize usable panel space. Successful processing of 600 mm PLP hinges on several factors. However, panel warpage control is the primary factor driven by die size, fan-out ratio, package height, and panel layout design. For our evaluation, we took a look at a test vehicle with 4.5 by 5.5 millimeter package size. This is a single die with one layer RDL with 350 micron ball pitch, 0.55 millimeter total package height, and solder alloy used is SEC405. Incoming wafer undergoes copper stud formation process, followed by wafer singulation, reconstituted onto a 600 millimeter temporary carrier prior to mold compression process. Die shift in X, Y, and theta is compensated during pre and post chip attach process prior to final mold compression process to ensure minimal die shift at mold dispense and mold compression. The temporary carrier is then debonded from the panel after mold compression process and undergoes a top grind process to expose copper studs. Warpage control requirement for the 600 millimeter fan-out PLP is as follows. TTV must be less than 50 microns, and panel warpage must be less than 1 millimeter. In this evaluation, 5 600 by 600 panels were used. TTV measurements were taken at post-mold cure and post-copper stud top grind. Warpage measurements were taken at post-mold cure. Both TTV and CPK measure was more than 1.33. One of the concerns during mold dispense process is die shift. Mold dispense optimization needs to be considered since mold material tends to shrink and gravitates towards the center of the panel. So I have here a little cartoon on your right hand side. Blue arrows show how mold tends to gravitate towards the center, and then the red arrows indicate possible die shift in X, Y, and theta direction. Die shift can be optimized by improving die placement at chip attach process and mold dispense pattern application. Now, we need to note that even if the TTV is well within specification, there will likely be slight die shift and would impact the RDL patterning process. To compensate the minor die shift caused during mold compression process, a laser direct imaging process during photolithography is applied at RDL patterning to ensure via to UBM connections are made. Here's a summary of the process evaluation for the test vehicle. CPK is more than 1.33, panel processing yield above 99%, shear mode is through bulk solder, and defects observed at final automated visual inspection are similar to wafer level CSP defects in a sense that we have foreign material, oversized solder ball, or solder breaching. Defects are marked as rejects on the panel map. The test vehicle was then subjected to component level reliability tests such as MSL1, unbiased has 96 hours, and temp cycle condition B. CSAM was performed after each test to ensure no delamination or voids occurred. Inline data for thin film processing through solder ball attach were collected, such as critical dimensions for passivation layer 1, RDL, passivation layer 2, and UBM. Conclusion derived from the test vehicle panels for 600 mm PLP shows that it passed JEDEC requirements for component level reliability and inline data collection meets specification. Additional board level reliability data will need to be completed to supplement CLR data. From the illustration courtesy of Yield Development, for a 8 mm by 8 mm single die on 200 mm carrier size, a cost reduction of 25% when migrating from 200 mm to 300 mm carrier can be realized. Further cost reduction can be realized when migrating from 300 mm to larger panel sizes. Regardless of the chip first or chip last option for fan-out, all platforms have one common target, which is cost. Now, within the cost constraints, one has to determine the context of application. Core markets such as baseband, PMIC, and RF normally fall within the 25 mm square package size with one layer RDL. This market normally uses chip-first platform. Larger body sizes, I would say above 100 mm squared, for example, like APE, networking, or high-performance computing, are best served by chip-last platforms. Although chiplet-like processing utilizing chip-first process is on the horizon. Key drivers for fan-out are body size and number of RDL layers. It is possible to have a body size less than 25 mm squared with 2-layer RDL. However, the cost of the fan-out package will also increase with the added RDL processing. So on the left-hand side of the slide, we took a look at fan-out technologies, including flip chip CSP and embedded die, and compared with price comparison. And this is utilizing a 6 mm by 6 mm body size. TSMC's Info brings technical solutions, but it's limited to TSMC silicon as a single source, hence holding back on its widespread adoption. In general, Info and M-series options are attractive as their packaging technologies are considered to be functionally equivalent. Now, on the right-hand side, I have a general guideline comparing body size versus RDL layers and cost. I will explain a little bit more about body sizes less than 25 mm squared. Package price or average selling price is highly dependent on the die size, number of die to be assembled during reconstitution, and number of RDL layers as it adds on to manufacturing costs and cycle time. For example, a die size of less than 1 mm squared may take upwards of 8 hours to complete the chip attach process on a 600 mm panel, as opposed to die sizes larger than 25 mm squared at less than 1.5 hours. Assuming all gantries are simultaneously picking and placing the die at chip attach process. The material, time, and cost consideration for smaller die sizes must be taken into account and may skew baseline pricing model. What we found is that the sweet spot in panel level packaging process for non-package on package is between 4 mm squared to 64 mm squared body size. Body sizes outside of this range will require additional process optimization. In summary, scaling up to 600 mm by 600 mm fan-out PLP becomes a necessity for lowering down costs and enables higher volume processing. A 25 mm squared package, when converted from a 300 mm round panel, can fit up to 5 times more die on a 600 by 600 mm panel. 600 mm by 600 mm fan-out PLP can be segmented into 4 sections to enable usage of existing solder ball attach, back grind, testers, automated final visual inspection tools with minor modifications. Component reliability for a 4.5 mm by 5.5 mm test vehicle was shared for 6-sided die protection. Board level reliability data is still pending completion, but is expected to pass JEDEC test requirements. All inline data and component level reliability data passed and meets process and product specification. Sweet spot in 600 millimeter by 600 millimeter fan-out PLP for non-package on package is between 4 millimeter squared to 64 millimeter squared for single die processing. Above 64 millimeter squared package range, warpage management and a combination of new process steps would increase the cost of manufacturing. We would like to express our sincere appreciation to the 600 millimeter fan-out PLP NPI team, process engineering, equipment engineering, and quality assurance team of Nepes Corporation for their helpful advice and support of this work. Thank you again for your attention. If there are any questions, feel free to submit through the portal.